Okay.
Okay.
So, hi everyone, and thank you for being here remotely. In this dissertation, we contribute a new direction for improving face-to-face remote collaboration with 3D digital content. First, for more than 30 years, I have been fascinated by the concept that people that are far, far away from each other could interact and as if they were sharing the same space by means of crazy technologies from science fiction. In fact, nowadays, video conferencing plays a huge role in connecting distributed families, connecting people that work together but are distant, connecting people that are not even working on Earth right now, and of course, connecting people that are physically distancing themselves because of this pandemic. So the main focus of this research was not simply facilitate communication, but it is to improve the ability of people to work and collaborate remotely. So video conferencing technologies are proven approaches. However, modern tools still uphold partial viewing or downscale representations of people. This reduces the sense of presence because conventional telepresence technologies interfere with the ability of people to use nonverbal communication. Because when people are together, they use facial expressions, gaze, body posture, and pointing to objects. And these are fundamental when collaborating. So for a telepresence encounter to be closer to a collocated experience, we should rely on a full upper body portrayal of people to allow for the understanding of nonverbal visual cues. And right now it is safe to say that the state of the art of virtual presentations of people are pretty good. And with that established, we can focus on the next step, which is collaborating in a shared workspace. Bill Buxton is one of the pioneers of telepresence. In early 90s, he contributed 3 really important concepts that are the foundations of all the following research. These concepts are the person space, which is where you look when speaking to someone that is remote, a task space as a place where the work appears. And Buxton also identified the reference space, a space where the person space and task space are so integrated that remote person could use non-verbal communication to refer to workspace elements. Well, in this particular scenario, the reference space is so limited because the person space and task space are totally separated from one another, which makes the experience far from seamless because of the big cognitive task of being constantly shifting between person and work. With this in mind, Hiroshi Ishii started experimenting with the way people could collaborate remotely away from the usual talking head scenario. And he identified 3 possible metaphors for people to come together and collaborate. A whiteboard metaphor, where people could be side by side facing a smart drawing board. This metaphor takes the advantage of a task space that is shared and is oriented to both participants, but people in a side-to-side formation have to be constantly shifting their attention between colleagues and whiteboard. This breaks the fluidity of the collaboration because people cannot perceive nonverbal cues. For that reason, face-to-face formation is more adequate. Ishii also talks about a remote encounter equal to sitting on opposite sides of a table, which is quite suitable for understanding nonverbal communication because participants can partially perceive face expressions and hand gestures. And of course, the workspace is upside down for one of the participants, making it difficult to understand what's going on. Therefore, Ishii settles on a glass window metaphor that profits from the non-existing necessity to shift focus between person and task. And unfortunately, participants do not share the same task space orientation, rendering all gestures meaningless. So to address this, Ishii and colleagues in '92 introduced Clearboard, implementing a glass window metaphor with a tight integration of person space and task space. And they used mirror reversing manipulations to correct gaze and pointing awareness in this 2D workspace. And since people are always face-to-face, there is no need to shift in attention during a collaborative session. But of course, this works focused on collaborative interactions with 2D content. Yet 3D objects are also important. The world is in 3D, and 3D models are used a lot in fields such as engineering and architecture. That's why in this dissertation, we propose an extension to the glass window metaphor, which is the above a table metaphor that renders 3D digital objects in a workspace between two participants and takes advantage for being face to face. Surely, 3D content adds a lot of problems to the collaboration because people are face to face and have contrary points of view, which means that there is occlusions that may invalidate the non-verbal gestures. So if it is difficult to understand spatial references, participants surely share a poor awareness of what's happening in the workspace. So this constitutes the problem of this thesis and our approach as different understandings of the workspace, occlusions, and it's difficult to establish spatial relationships. And to overcome these issues, our proposal was to individually manipulate their perception for them to share the same understanding of the workspace by presenting to each participant altered versions of the collaborative space. So our research statement is: perception manipulation can be used to increase workspace awareness and improve face-to-face remote collaboration in shared 3D workspaces. This research statement has been divided into 3 questions. The first one: can 2 opposing collaborators share the same perspective as of a 3D workspace? Can perception manipulations improve the understanding of nonverbal communication? And can 2 opposing collaborators share the same understanding of a 3D workspace? And to address these questions, we made 5 significant contributions. The first 2 were mainly focused on establishing the theoretical foundations and insertion technology, and the remainder 3 contributions were specially targeted to answer the questions that comprise the research statement. First, we contributed the theoretical grounds for using perception manipulation to improve remote collaboration, which is how we apply perception manipulation to remote collaboration. We contributed an open source toolkit for body tracking and capturing virtual avatars, and an assessment for different manipulation techniques to study awareness in a 3D workspace, resulting in a proposal of a design space called the negative space. We contributed novel body warping techniques to improve the interpretation of pointing gesture. Results suggest that manipulating pointing arms can significantly reduce misunderstandings about the target's position, thus improving collaboration. And finally, we contributed an approach to integrate person space, task space, and reference space for face-to-face remote collaboration. And results suggest perception manipulations were adequate in achieving a common understanding of the workspace and participants' nonverbal cues. So in what follows, I will be presenting our theoretical approach for applying perception manipulation to remote collaboration, our open source toolkit to rapid prototype interactive systems, and also the 3 use studies focused on answering our research questions. And I will finish my presentation with conclusions and future work. In terms of theory, our hypothesis is simple. Improve the awareness remote participants have of the collaboration using perception manipulation techniques. Starting with awareness, Gutwin and Greenberg contribute to the framework, saying that awareness can be divided into 4 major concepts. The first 3 are offered for free if participants are able to see and hear each other. And that's why we focus on workspace awareness, because it is the one that we can manipulate to improve collaboration. Workspace awareness has 3 requirements that we have to take into consideration. The first is fit-through. Fit-through is the ability to perceive how the artifacts within a workspace change as they are being manipulated. That's why it's too important to deal with occlusions. Consequential communication relates to the perception of where people are looking and if their actions can be understood by seeing the performance of that action. And finally, intentional communication happens when people are able to include gestures to qualify verbal references to artifacts on the workspace. So these are the 3 elements that we focus to develop our perception manipulation techniques. And to manipulate perception, we can exploit the dominance of vision, which is a technique utilized in virtual reality. It is a sort of illusionism to trick people, as Mandian and colleagues tricked people into thinking that they were manipulating multiple objects, but in fact they were only manipulating a single cube. They did this by resorting to warping the user's own body representation in combination of warping the world too, so to minimize the effects of both techniques. Our first technique is forcing a shared perspective. Collaborators are at the opposing ends of a workspace, yet they have the same overview. This concept uses transformations that enables opposing collaborators to share the same point of view of a shared workspace. The second is workspace warping, corresponding to any manipulation that changes the properties or the representation of the workspace to translate remote people's actions to the local reference space, including geometrical transformations such as mirroring or dimensional inversions. And finally, body warping, corresponding to any transformation that entirely or partially changes the properties or appearance of virtual representations of people. We consider body warping when virtual representations of people are reshaped and transformed, but without changing the meaning of the gesture. With this, we can move forward and talk about the technology built to support all this. There were a lot of toolkits around, but they did not support body representations that could be manipulated by us. That's why we developed the Creepy Tracker Toolkit, an open source tool that not only supports rapid prototyping user experience, but also facilitates the design of remote collaborations. Our tracker uses multiple depth cameras to track skeleton models. And of course, it provides a stream of point cloud representations of people. Therefore, we contribute an effective tool to prototype interactive telepresence scenarios. And we exploit this tool to prototype all the following user studies in the third part of this presentation. So now I'm going to introduce the 3 user studies developed. First, an assessment to see how manipulations could improve workspace awareness. Then we propose a method for improving pointing gestures. And finally, we propose a technique to reshape gestures and interact face-to-face in a shared workspace. But first, we focus on investigating the workspace awareness. We chose to manipulate certain characteristics of the collaboration. We manipulated point of view to investigate shared perspective, embodiment to investigate body warping, and workspace to investigate workspace warping. For this, we proposed the negative space, which is a virtual space connecting 2 remote rooms via a sort of a tunnel. In this space, we encounter a virtual 3D workspace. We devised 4 conditions. The first one was a veridical face-to-face scenario. Both participants could see each other and the workspace as if they were in opposite ends. This condition was the baseline. In the second condition, participants shared the same point of view of the workspace in a way that simulates a side-by-side approach. In the third condition, participants shared the same point of view, yet the embodied representation was horizontally inverted to match the reference space, meaning that pointing gestures would match. And finally, in the last condition, participants also shared faithful face-to-face embodiment representation of each other, but the workspace was horizontally inverted. We devised an evaluation task where an instructor aided an assembler into solving a simple brick puzzle. 8 pairs of people were recruited, and we gathered metrics for task performance from logged data, such as completion times, wrong selections, and wrong moves, and user preferences from questionnaires. We found a tendency for completion times to be smaller when just mirroring the remote participant, but found no statistical differences. We also did not find any significant differences in relation to wrong selections or wrong moves. Yet, user preferences using a questionnaire, we found statistical differences using the Wilcoxon-Seinerang's test. So instructors reported that mirroring the workspace was more difficult than the conditions of simulating a side-by-side behavior or just mirroring the remote person. Also, it was easier for instructors to explain the position where to put the next brick with the remote person mirrored. With this evaluation, we found that mirroring workspaces is too cognitive demanding for people to interact with, but conditions with a shared point of view were preferred. However, we also found that people have a huge difficulty in interpreting pointing gestures to distant objects. That's why in the second study, we addressed this issue and proposed the method for improving pointing gestures. And of course, our approach was to improve pointing perception by using body warping. Pointing to objects that are close to us have no issues because we can touch and target, we can touch the target objects. But there is not the case for distant objects. The gesture of pointing to distant objects is hard to interpret. Also, it can cause misunderstandings. A study from Herbert and Condi suggested that people systematically misunderstand pointing gestures because people perform pointing gestures and interpret them in different ways. Pointers seem to place the index finger on a line connecting the eye to the target. However, to interpret the gesture and determine the target, observers interpreted pointing gestures by extrapolating the target using a vector defined by the arm and the index finger, which at a distance will be something completely different. So if someone wants to communicate target A, it's annoying that other people realize B as being the target. So if without any manipulation, people do not realize that this guy is pointing to that target, because they are looking at a completely different location, our approach moves the arm to the right place for people to observe the correct target. We called our approach warping the axis. So to evaluate our approach, we conducted an evaluation with 18 participants who participated in pairs in a virtual reality environment. In 2 different conditions, we evaluated warping the axis against normal pointing, and participants alternatively took on the role of pointing person and interpreter, and the pointer was the only one capable of seeing the targets on a pole. We obtained the mean distances of the errors for each condition on 3 pole distances. Results from a 2-way repeated measures ANOVA showed that all effects were statistically significant. Overall, the main effect suggested that our approach was superior in task performance, although performance in both conditions declined with distance. A pair t-test showed significant differences between 1 and 2 meters, 1 and 3 meters, and 2 and 3 meters. The interaction effect between distance and technique was also significant. And knowing that the 2-way ANOVA demonstrated significant differences, we applied a post-hoc pair t-test for each distance. And our approach demonstrated a significant error decrease at 2 meters and at 3 meters too. So we also looked at the user preferences using a questionnaire that showed no difference whatsoever, leaving us to believe that our warping method was not noticeable. So the findings suggested that our approach reduces perception errors and it is not noticeable, meaning that body warping does improve collaboration. This work was published in CHI last year. And in CHI this year, Mayer and colleagues will present an expansion to this evaluation that corroborates our findings for other dimensions. So finally, we can proceed to the last user study of this dissertation. And in this last step, we proposed a technique to reshape gestures and interact face-to-face in a shared workspace. For this, we went back and revised the proposed manipulation techniques. We now know that sharing the same perspective and doing body warping is favorable, but we also found that workspace warping should only be limited to rotations and not mirroring or inversions that make the workspace difficult to understand. Therefore, we proposed a new approach for a workspace that enables collaborators to share the same perspective, while their gestures are reshaped to improve the awareness of what is happening in the workspace. We call this approach altered presence, where when in a shared workspace, whenever a collaborator interacts with the workspace, the avatar is altered, warped, or reshaped to match the observer's perspective of the workspace, and then achieving a reference space in the above the table metaphor. To be more specific, when a local collaborator interacts with the workspace, a copy of that person will appear remotely. This is a mesh created with a point cloud provided by the Creepy Tracker toolkit. And to match the gesture to the local reference space, we first do a mirror reversing of the remote person. Then we use inverse kinematics to calculate where his pointing arm should be, do a little body segmentation of the person's limbs. And finally, we apply rotation transformations to reshape all that point cloud into a convincing new gesture. Here you can see how this body warping is done in a virtual person. The position of the red spheres are calculated from the simple inverse kinematics algorithm, and the rest of the arm is reshaped to match those calculated values. So we built this into a virtual reality scenario, merging two workspaces to perform a user study. In our user study, our hypothesis was that imperceptible distortions can be beneficial to remote virtual collaboration without negatively impacting task performance. And we recruited a total of 12 participants. The participants were asked to switch between the roles of instructor and operator, where an instructor had the responsibility to identify a point of interest within the workspace, and the operator was asked to put a virtual marker demonstrating his interpretation of that point of interest. We employed three evaluation conditions: a face-to-face condition with our approach, participants in opposing sides of the workbench sharing the same perspective of the workspace, a second condition where participants were in opposing sides of the workbench with opposing points of view of the workspace, and finally, a side-to-side formation, therefore sharing the same perspective of the workspace. We looked at task completion times, error distance, body rotation, using logged data, and user preferences using a questionnaire. In regards to completion times, there was no difference between conditions. For error distance, we found that being side by side is the best, but no statistical difference were found, suggesting that with altered presence, people perceive the intended region within a margin of error. Regarding to body rotation, a repeated measures ANOVA corroborated our assumptions that our approach does minimize the shifting between task and person space. Again, results from a user preferences questionnaire revealed no difference between all conditions, suggesting that our approach may feel somewhat natural. Therefore, our approach ensures that opposing participants share the same perspective and distorts gestures performed by a remote person to present a corrected virtual representation of those gestures to the local collaborator. And now I will finish my presentation with conclusions and future work. Well, looking back to the research statement, we can conclude that this research statement was proven because perception manipulations can indeed increase workspace awareness and provide remote collaboration. By forcing a shared perspective and reshaping people's gestures to match a local reference space, we can create a common understanding of what's happening and seamlessly, because there is no need to shift between task space and workspace. So let's look at the accomplishments of this dissertation. First, we contributed to the theoretical grounds for using perception manipulation. We contributed software for body tracking and capturing avatars. Our assessment of workspace conditions concluded that people are indeed able to interact with a shared perspective scenario. Body warping can be used to improve the interpretation of gestures. And the combination of all these things results in a shared understanding of the workspace. So did we answer our questions? I think so. The first question was about if opposing collaborators could share the same perspective. And the answer is yes. Participants in the user studies preferred and were able to interact while sharing the same point of view. In question 2, we asked if perception manipulations improved the understanding of nonverbal collaboration. And yes, because warping the axis improved pointing gestures and reshaping made it possible for people to understand regions of interest. And in the last question, we looked for if opposing participants would share the same understanding of the workspace. And again, yes, to a certain margin of error, participants were able to convey to their colleagues the intended position within the workspace. So finally, in terms of related work, future work, I found that both our negative space and altered presence approaches should need more exploring and perhaps evolve to an approach focused on merging and blending remote spaces into one, blurring the lines of what is local and what is remote. In a more technical note, there is room for improving body warping. And of course, what I would like to research next is using warping techniques for people to watch their bodies performing complex tasks and maybe learn how to do these new activities. So during the work of this dissertation, I was involved in 19 publications, some as first author, but I would like to single out these three. The Creepy Tracker Toolkit published in ISS, and the first two studies, Negative Space in VRChi and Warping Dexes in Chi. The last part of this dissertation will be published as well, I hope. So with this, I conclude my presentation. I would like to give my thanks to the members of the jury, especially to my advisors, Rick and George, all my co-authors, and to all faculty, staff, colleagues, and friends that are members of the VIMI research group. So thank you all.